Okay, everybody, what we're going to do in this video is we're going to go over the dynamics of a circuit that includes an inductor in it. So what we've done before, okay, is we have patched together in series a resistor and a capacitor, right? So when we did this before, we saw that we could affect the timing, the dynamics of a circuit by putting in a resistor and effectively slowing down the process of charging or discharging a capacitor, right? So having control over this timing gives us more control over what happens in the circuit dynamics, okay? What we're going to do now is we're going to add an inductor into this series combination, and this will be called an RLC circuit, okay? So this is RLC circuit. Now, what's important about this is that let's take a look here at the different parts and what will happen just taking each one individually, right? Let's say just the resistor. So if we focus on just the resistor, when we hook up some voltage source, let's assume right now that the voltage source is DC, so just a direct signal of voltage over this resistor, then what will happen is it will slow down the flow of current. It'll resist the flow of current, right? But it'll do this linearly. So we have our formula V is equal to IR. How much charge is flowing over depends on how much resistance I have linearly. So this is great. Now, let's take a look at our capacitor. So a capacitor was another element that we've already looked at. And we know that if we hook up some DC voltage source to this, that it will charge, right? So it'll charge on either side of this plate. And the important thing here is that when it's done charging, no more current will flow. So that was very important when we did RC circuits, was that my resistor slowed down this process, but eventually, once we hooked up our battery, eventually our capacitor became fully charged and the current stopped flowing because it can't flow around a complete circuit. It can only flow up to one side of my capacitor and to the other side of my capacitor and then just meet up there. Okay? So, last thing here is our inductor. So, for our inductor, we already know that when we initially hook up a DC voltage source, a direct voltage source, to my inductor, it will create a magnetic field inside, which creates some electric field which tries to stop my currents, right? It'll impede the flow of current when it does this. So in the beginning, you have very little to no current flow, but then as time goes on, the current will increase. So now we have something very interesting here where, all right, this is a linear part, but I have these two pieces right here that are essentially fighting against each other, where when I first connect my circuit, if I'm just talking about a DC constant voltage source, this inductor will not allow current to pass, right? It'll resist the current a lot in the beginning, and then over time that'll fade. This capacitor will first allow current to flow, but then once it starts charging, then it'll slow down and it won't allow current to pass, right? So these two things are kind of at odds with each other. So what happens now when we connect our circuit with all of these elements together, right? So why would we do this? So when we do this, we have this fighting source of impedance, okay? Impedance now being the word that we're going to use. It's a little bit more general than resistance. Resistance, yes, my current is slowed down, but it's done linearly. Impedance is going to be slowing down my current, or slowing the flow of charge according to these nonlinear objects, right? So if I hook up a DC voltage source to this circuit, it won't be very interesting. What's going to happen is current's not going to flow very well, okay? But then it's going to start to flow, and then it'll eventually stop flowing again, right? So it'll do this where my current will start to flow, but then it'll kind of drop off again. In this point here, Sorry, let me go ahead and label some axes here. This will be current, this will be time. So on this graph here, I start off with a very small amount of current because my inductor is stopping me. And then I start to build more current. I can pass through this inductor, but now I start charging my capacitor, and then so my current will go down, right? So I have this kind of curve here. So it's not very interesting if we hook this up to a direct source, but now we're going to have an AC source, an alternating current. So what that means is it's going to flip back and forth. So this, let's say this is my positive, this is my negative, and then it will flip its source where this is my negative and this is my positive. And it'll do this with some frequency, right? So it'll flip its voltage source with some frequency. This is AC current. This is the current that we normally use. If you talk about outlets in your house, things like that, these are driven by AC current. So we have now this curve will happen over and over again, right? Where my first signal might induce this part of a wave, and then if I wait till it's almost done, but then I switch my current, it'll happen again. So it'll create some wave that repeats over and over like this, okay? So what we want to do is we want to build a circuit that essentially has maximum current only at a certain frequency. So doing this really allows us to control what frequency of current is allowed in my circuit. It's a filter. That's the important thing to remember here, is this circuit right here acts as a filter. The timing, depending on how much inductance, how much capacitance, how much resistance we have in here, we will have the timing of our circuit will be affected such that only certain frequencies from my power source are allowed to go through this circuit with the minimum amount of resistance. Everything else is going to be like this region here, but when we have the right timing, the right frequency, we'll get a maximum amount of current, and we're going to call this resonance, right? So it's a really good filter. So what you can do with this is you can allow certain frequencies of signals to come into your circuit, right? Think about radios, think about TV, like antennas, these things. They're receiving frequencies of signal, right? So we adjust our components to only let certain frequencies through, right? Otherwise, you're just getting everything, and then you have no signal. It's just going to be noise, right? So that's what these circuits are for. So in order for us to talk about them, we have a little bit of vocabulary that we're going to go through. I'm not going to go through the formulas too much. I'm going to let you know what each of the pieces are. But the important thing here is just to kind of understand the process of what's going on. So impedance, like I said, this is our new definition for resistance, but now with some AC component for inductance and capacitance, right? So here we can see if I just cover up, okay, this part here, then you'll see that I have, so if I didn't have an inductor, I didn't have a capacitor, well then my impedance would just be the square root of R squared, so that would cancel and just give me R. So my impedance would just be my resistance if I didn't have these things in here. But I have some resistance that comes from my resistance to charge flow, which comes from my inductor. This is going to be this inductive reactance. And then I have some resistance to flow of charge that's going to come from my capacitor. This is going to be called capacitive reactance, okay? And they're given by XL and XC. And so each one of them is just based on the frequency of current that you put in. Sorry, this will be, the angular frequency of current that we put in. And then the magnitude of inductance for my inductor, or 1 over the angular frequency of current multiplied by my capacitance, right? So these are pretty straightforward. Now, this here, my angular frequency is just 2 pi times my frequency here. This would be, let's say, the frequency of my incoming signal that I want to filter through, or the frequency of my power source, how fast it's changing its frequency, right? So we're going to do a little bit of a trick here to kind of show how this resonance works, right? How do we get this peak right here? Well, if we want to get this peak, we need to minimize my impedance. Okay, so I'm going to show you how we're going to do that. If I set XL equal to XC, then this XL minus XC is going to go to 0. If that happens, then all I have is my resistor, and my impedance goes away. Now I just have resistance, right? So this is my minimum resistance to charge flow that I can get. Okay, so here my impedance will be minimum. It'll just be equal to my resistance. So what I'm going to do is I'm just going to set these equal to each other. I have my formulas here. I'm going to set them equal to each other. And I'm going to get my angular frequency on one side by itself. So it becomes omega squared is equal to 1 over LC. And so this omega, once I get it by itself, this is my special frequency when these two things are equal, which means I have my minimum impedance, okay? And that's equal to 1 over the square root of L times C, okay? So here I've kind of outlined, if you look at this as Ohm's law, but now what I've done is I put this as an AC voltage, and instead of R, I've put in Z here. If I want the maximum current, then I need the smallest Z, because I have I is equal to my voltage source over Z. If I make Z very, very small, then my current will be the largest, right? Okay, so that's what we're doing. We're trying to make Z as small as possible when we set XL and XC equal to each other. Because you can see here that no matter what comes out here, it doesn't matter if it's minus 10 or 100. It doesn't matter if it's negative or positive, whatever value comes out of subtracting these two things. Once we square it, it will always be a positive number. And then if I add a positive number and a positive number and square root it, it'll always be bigger than whatever R is by itself, okay? So my minimum is just getting rid of that term. So when I do this, I have the maximum current in my system. I've reached this sort of resonant point, okay, in my using some frequency, using my resonant frequency, okay. So this resonant frequency, so this is my resonant angular frequency. Just turning this back into a linear frequency, this would show what is the frequency of the signal that is not going to be filtered. So everything else is going to be filtered except for this. Okay, everything else is going to be attenuated downwards and made smaller, or we could say quieter signal, except for this frequency, which is going to be allowed to pass through without that extra impedance.